Hello everyone, I'm Yuanlong Chen, and this is joint work with Bowen Zhu, Bingxian, and Yichuan Wang. We present a lightweight MPC controller for brand auction ads. The idea is simple. Learn a local monotone bid response curve, map the current pacing target to a bid, and then repeat after each interval. The result is model-based, interpretable, and practical to serve. So why brand auction ads? Performance objectives such as clicks and conversions often produces sparse and delayed feedback. Brand objectives, including impressions and video views, are much denser and faster. The timelines here show this contrast. A recent window of pacing intervals can therefore containing enough information to estimate the next interval response online. This lets us use a small local model instead of serving a high-dimensional bid landscape model inside the control loop. We begin with max delivery under a lifetime budget. Under standard auction assumptions, the impression level bid separates into the predicted value and one campaign level multiplier. The serving system already estimates the per impression value. Our controller updates only this multiplier once per pacing cycle. So we reduce the control problem to one question. Given the remaining budget, predicted supply, and recent delivery, which multiplier should we use in the next interval? Here we show one step MPC method. It has four steps. Step one, we read the remaining budget and predict the supply. And step two, we compute the next interval target spend. The formula here allocates the remaining budget according to the next interval's share of expected future supply. So the target remains lifetime aware. Step three, we then fit the spend response from the recent data. And finally, last step, we choose the largest bid whose predicted spend stays within the target. So here in the plot, we start from the horizontal target line, and then we move to the fitted curve, and then drop to the bid axis. We then apply that bid, observe the spend and results, update the window, and solve again. Although the action horizon is one interval, this repeated feedback and reoptimization preserve the receding horizon behavior. So now we estimate the response with isotonic regression. So here, each gray point is one completed interval, bid on the horizontal axis and realized spend on the vertical axis. The observations are not noisy and may violate monotonicity, as you can see here. But for a locally stable auction population, a higher bid can only expand the set of auctions we can win. So expected spend should not decrease. PAVA here, the pooled adjacent violator algorithms, merges the labeling violations to produce the blue monotone fit. The original line here is the target spend, and the red line here marks the largest feasible bid. We interpolate within observer range and use controlled extrapolation during cold start. This produces a one-dimensional model that is cheap to update and easy to inspect. As for cost cap campaigns, the same structure needs one additional response curve. We fit both the predicted spend and predicted results. The controller then selects the bid with the most predicted results, subject to two conditions here. One is the predicted spend must stay within the interval target, and predict cost per result must stay within the residue cost target. Spend and result here are individually monotone, but their ratio may not be. So we therefore apply a simple grade feasibility search over bids. And the serving loop remains small, transparent, and fully online. In 100 offline simulations, MPC here matches the Oracle constant bid benchmark. its CPV is around 0.01319 compared with the 0.01318 for the Oracle. And it improves on the PID controller and dual grand descent. MPC also substantially lower bit variance, while all other methods achieve nearly full budgetization. So the gain here is not from spending less. The key mechanism is direct target to bit conversion, which reaches a efficient bit with less oscillation than updates based only on the realized pacing error. Finally, we also run a 7-day within campaign budget split experiments against the production controller. We hold the other production components fixed. So here, positive lift is better for budget utilization. Negative is better for CPM, CPV, and bit variance. We can see that both max delivery and cost cap campaigns improve. The largest efficiency gain here is a 2.97% reduction in CPV for cost cap campaigns, and bit variance falls by about 2% in both settings. So here, all reported effects are statistically significant at the 5% level. So overall, the main takeaway is dense brand feedback enables a small interpretable controller that improves pacing and cost efficiency without an additional model serving dependency. Thank you.